Share my screen. Again, yes. Morning, everybody. As we get started here, quick reminder, 2 handouts. The first handout should look like this document here, says sorting notes at the top of it. And then the second handout is a printout from Wikipedia, this page on the master theorem. And if you scroll down here, it should start like this generic form. This whole section down here is the thing that's being printed out. And this entire section right here, this entire printout, this 2 pages front and back that you have, is the full statement of this master theorem. We'll be going over that in class today, and I printed it out for you because eventually, once we have all the tools that we need for runtime analysis, you'll be doing quizzes on the master theorem here, and so you'll need that printed out copy. But it just comes straight from Wikipedia here. So again, yeah, 2 handouts, the sorting notes handout at the top and the master theorem notes. This week in class, we're going to be doing 2 topics, more recursion. And in particular, we're going to be using this master theorem to prove things about our runtime. And we're also going to be starting to talk about this idea of sorting. If we recall from last week in your homework that's due tomorrow, we really like data that is sorted because it lets us do binary search on the data, get the logarithmic runtime instead of the linear runtime for searching. And from your lab that you did on Friday, hopefully that has emphasized for you the huge importance of this logarithmic runtime and how much faster it is than the linear runtime. So yeah, again, this week we'll be going over this sorting topic and how we actually get that data sorted in the first place so that we can do the binary search. A couple of quick announcements today before we get into the technical stuff. So first thing is an issue that I posted. We have 2 announcements here, 2 events this week that are going on. The first one is today. The math department's doing a series on getting to know the different math professors. And so Mark Huber is talking today in the Bauer Center South 22. It's just like right over that way a little bit. And lunch is provided for this. He's talking about exactly what it means to be a number. So I'd encourage you all to come to that if you're available and get to know Professor Huber and some of the other math professors. Also this week, another event on Friday, I will be talking about the time I spent in North Korea. I spent again about 2 years in North Korea. And so that'll be this Friday from 7 p.m. to 8:30 p.m. So late at night, founder's room of the Bauer Center. So not this building, but that building over there. And this event is part, I guess, the Friday meetings is a regularly scheduled meeting of the 5 Cs University Club, which is a Christian club. And so I'm going to, in particular, be talking about what it was like to be a Christian in North Korea and yeah, how the religion and international relations things interacted with each other. Any questions on those announcements before we get to technical things today? Or questions about anything administrative at all in the class? Okay. Your homework for this week is posted. It's going to be specifically on implementing these sorting algorithms. You can find it up here we're again in the topic 5 sorting folder for our class repository. I think most students find this sorting algorithm to be, or this sorting homework to be much easier than the last 2 homework assignments. I tried to time this week's assignment so that a lot of people I think have maybe midterms going on right now. So you have a little bit of a lull in this class this week. If you do have time, though, I definitely recommend reviewing your Vim and getting a good workflow set up in the terminal. One of the things that I've just noticed during lab sessions is a lot of people still using your tools very inefficiently, just spending like an hour, half hour this week of getting a little bit better at those tools will really pay off again for the whole semester here. Yeah, you're going to be the last 2 weeks especially, hopefully have given you a sense of how much you'll be using Vim and the terminal. And so the better workflow you get on things, the better the rest of the semester is going to go. If you go on after this course, take more upper division CS courses, all of those courses will be in Vim and the terminal. And so you'll be having to use these tools a lot. And a reminder that in computer science, in the hacker world, boredom and drudgery are evil and laziness is good. So you should try to be cultivating while you're working with these tools, this attitude of laziness. Just like Bill Gates, that he always wants to choose a lazy person to do a difficult job because a lazy person will find an easy way to do it. If you don't know who Larry Wall is, he's one of the more famous programmers from the 90s. He wrote the PHP programming language, which is what Facebook is written in. And you can see here that one of his chief virtues of being a programmer is laziness. And again, people often I don't know, feel weirded out that a professor is telling them to be more lazy. But in the computer science world, what it means to be lazy is to use your tools efficiently so that you're not doing the same task over and over again. If you find yourself switching between windows over and over again, then you're not being lazy. You're doing too much work. You should put your windows side by side so you don't have to switch between them. Or if you find yourself in Vim just constantly in insert mode, moving around with the keys, then you're doing too much work. You should be more lazy. You should get out of insert mode and use the shortcuts. Okay, so now onto actual technical material. We're going to start by, this is the notes.py file from last week that has our sequential search algorithm inside of it. Go ahead and bring that up. We're going to go into binary search today and get our actual analysis going. Again, last week we talked about the implementation of binary search, getting some intuition going through Python Tutor about what it does. And then in your lab, you saw that binary search is in fact much faster than the sequential search. We stated that binary search has this logarithmic runtime and that sequential search has this linear runtime. But we're going to more formally work through that now and prove that and discuss why exactly that is, and hopefully get you a sense of when you're writing your own algorithms, how you can achieve these binary runtimes. Sorry, these logarithmic runtimes like binary search. So again, the file that we're currently on here, the notes.py PDF file, and we're going to go through the binary search. And in particular, the very last page, let me zoom in here for us. The very last page here, this binary search recursive 2 algorithm. This is the one that we're going to discuss in detail today. Any questions on where we're at before we get started here? Okay. So anytime we're talking about the runtime of an algorithm, we always have to know what the data structures are or what the types of the variables are that are being passed into the function here. So again, we have 2 variables up here, this xs and y variable. And we're going to start by thinking about what is the case when xs here is this array data type. We were introduced that into our lab last Friday, this np dot array. And again, arrays are very, very similar to lists. The only difference in the runtime between the arrays and the lists was that for the array, slicing is constant time, or O of 1 time, because there's no copy made. But for the list, the key difference between the array and the list, For the list, slicing makes a copy, And so the runtime, if we look at our sheet again with all the runtimes, it has it listed as O of K, where this K is the size of the slice right here. And if you recall from the lab, you had to run this code right here on both the array and the list. And it was really slow when you worked on the list, and it was really fast when you worked on the array. And so we're going to see more formally why that's the case right now. Okay, so again, we're working on the array first. We're starting with the array. Let me switch to green here. So I'm going to do all the array stuff in green here, going over the runtime. Then after we do the runtime for the array, then we'll go over it with the list, see exactly what the difference is and why the array is faster. When we have, so our recursive algorithm right here, the first thing that we'll always see in the recursive algorithm is the base case. So right here's the base case. We know this is the base case of the algorithm because we have the return statement right here, and the return statement does not recursively call the function. So this is the spot where we're going to stop doing those recursive calls. And here we only have one operation on the container, this length right here. This is our operation that's going on. And the length is just a constant time operation. So this whole thing right here is going to take time O of 1. Line 18 through 24 now, going into the recursive cases. We have our recursive call down here. And so we have another length call right here. That'll be an O of 1 operation. And then we have some indexing operations. Again, the square bracket right here. When you see the square brackets on the cheat sheet that you had of the runtimes, this was the get item runtime. And for both the array and the list, the get item runtime was constant time. So the if statements right here will happen in constant time. O of 1, O of 1 for both of these if statements right here. And actually this if statement down here as well, also constant time. All three of the if statements themselves take constant time. Inside of the if statements down here, so line 20 and 22, inside of these if statements is where we have these recursive calls. And again, we know they're recursive calls because they're calling the function binary search recursive 2, which is the function that we're analyzing right now. They're calling the function inside of itself. So that's what makes it recursive. And before we get to how to deal with that, we have one more operation right here. We have the slice. And again, we said that for the arrays, the slice takes constant time. O of 1, and this one right here, the slice is O of 1. So everything's taking constant time for us with this array. And now we just have to figure out how do we actually deal with the recursive call right here. How do we deal with this? Before we talk about how do we deal with this, are there any questions on what we've done so far? Any questions about why everything is constant time so far? Question? So the question is, why is this recursive call constant time? And the answer is that we haven't talked about this recursive call yet. It'll turn out not to be constant time. What is constant time is the list slice that happens before the recursive call right here. This excess square bracket right here. This is happening before the recursive call because we have to compute this in order to pass it into the binary search recursive function right here. So this is the key hard part of the problem and the thing that we haven't talked about yet, but we will talk about right now. So in order to do these runtimes, the traditional way to talk about it, any recursive formula, is that we're going to introduce a new variable called t. And we'll say that t of n will be defined to be the runtime of our function. So in this case, it's the runtime of the binary search recursive to function, just the runtime of whatever function it is that you're working with. T is, I don't know why they chose the letter T, but it's just the traditional letter to use when talking about the runtimes of recursive functions. And what we're going to do is we're going to write this out as a formula based on itself. So here, if I say, I'm going to write out a formula right here, and then we'll explain exactly where all the pieces of this formula came from. T of n equals T of n over 2 plus 1. So it turns out this is going to be the recursive runtime formula that corresponds to this binary search function up here. And we'll explain now why exactly that's the case. The first part, the easy part over here, is this plus 1. This corresponds to all of the non-recursive operations in our function. All non-recursive operations. And so these are all the things that we had in green up here in this code. So our base case, all the if statements and the things that happened inside the if statements. And up here, we were writing it in asymptotic notation with this O of 1. Again, when you add all of these O of 1s together, and again, we're adding them because they're sequential operations. First you do one, then another. They're not nested operations. There's no for loops here. So they're all sequential. We add them all together. And when you add things that are O of 1 together, you still just get O of 1. Notice that I'm dropping the asymptotic notation here. So I'm dropping the big O in this case. And if you were using theta or omega, we'd be dropping that as well. Since this is just an introductory course to runtime analysis, we're sort of skipping some of the technical details about like why it's okay to drop the big O here and what the more, but we'd have to do a lot more bookkeeping work in order to fully understand why it's okay to drop the big O here. And so if you want to work through that bookkeeping with me after class, I'd be happy to do that. But it's the easy thing is just you drop whatever your asymptotic notation is and put what's inside of the O. So just a 1 for us in this formula. And then why do I have this T of n over 2 over here? This corresponds to the recursive call itself. This is the recursive call. And I have another T inside of here because there's exactly one function called binary search recursive 2 that I'm doing that goes back to itself. That's where this comes from, this T right here. That the runtime of this function up here depends on the runtime of this function right here, which happen to be the same thing. So that's why we have the runtime of our function depends on itself over here. But where does this n over 2 come from inside of parentheses? It comes from the fact that our slice over here, this colon mid right here, this mid is the midpoint of our list, defined to be the midpoint on line 18 right here. And so we're dividing the size of our list by 2. The size of this slice, the size of our data structure that we're working on is no longer going to be n. It's going to be n over 2 when we work on this recursive call. So it's n over 2 right here because the size of this, size of the slice is n over 2. Hopefully that gives you a little bit of intuition about where this particular formula is coming from. We're going to see a couple more versions of these formulas today in class with different versions of code. And when we do that, you'll have more examples of how to construct one of these recursive formulas like this. But our next step, rather than seeing more examples of constructing a formula like this, our next step is going to be to actually see how can we solve a formula like this. Before we go on to actually solving this formula, are there any questions about, yes? Question is on the cheat sheet, the Python wiki runtimes. where is the array listed? And the answer is that the array is not listed. This np.array here is not built into Python. Not built in to Python. Comes as part of a library called NumPy. And so in order to get a full list of runtimes, we'd have to look at the NumPy library. There's a link on the lab from Friday that introduced the array about where to find that. But the key thing, the one thing to know about arrays is that slicing is constant time. That if you know that, then everything else is going to be the same as lists. Good question. Any other questions at this point? Okay. So how do we solve this? And by solve this, I mean get rid of this recursive definition over here. Make this just t of n equals something without a t on the right-hand side. We're going to see two ways of doing this in class today. The first one is called iterative substitution. Iterative substitution. This one, for a lot of students, is more intuitive about how things work. It's also more general in that this is something that you can always do, but it's also more work. So we're going to do just one example of iterative substitution here. And then we're going to, after we do the iterative substitution, we'll take a look at this master theorem, which again is this Wikipedia page that you have printed out. We'll take a look at how to use that and how to apply this theorem to sort of do all the math details for us automatically. The idea of iterative substitution is that we already, so if we had a formula for t of n over 2 right here, if we had a formula for this thing over here, we could just plug it in and then we'd have a formula for everything. And it turns out that we sort of kind of do have a formula for t of n over 2. That if I take my original formula, this formula right here, and substitute n over 2 for n, then I'll get another formula. Equals t of n over 4. So substituting n over 2 for this n right here, we get n over 2 divided by 2 is n over 4. And then plus 1. This whole thing in parentheses right here, that whole thing in parentheses corresponds to the recursive call up here, this t of n over 2. And then this plus 1 at the end over here corresponds to this plus 1 over here. So what I did was I just substituted in for, again, we have this formula, our original recursive call right here. And this parameter, I substituted in n over 2 instead of n, and it gave me this formula in red down here from this orange formula up here. I'm going to simplify this next, and we'll get that's equal to t of n over 4 plus 2. I'm intentionally leaving a little bit of white space over here. I'll come back to that in a minute, and we'll fill it up. And so now we have a formula for t of n over 4, or we need a formula for t of n over 4. How do we get it? Well, we can get it by, once again, substituting n over 4 into our original equation. So t of n over 4 like that. If we substitute n over 4 right here, we get that that's equal to t of n over 8, n divided by 8. And then again, plus, oops. I apologize. I'm wanting to move this equation that I started right here. This is what I was planning on putting over here in the left. I got ahead of myself, so I'm going to just undo this stuff right here and rewrite it over here on the left. So undo that. T of n over 4 right here. Substituting in gives me the T of n over 8 plus 1. So this equation right here in red, coming from this equation right here, substituting the n over 4 in for the n. When we do that, we get n over 8 right here, and then the plus 1 right here. Yeah, question is, why do we only have a plus 1 right here and not a plus 2 like we had over here? That's yeah. If we bracket that out like this, we'll get a plus 1. This stuff in the parentheses right here corresponds to the substitution, and then the plus 1 right here corresponds to that plus 1 right there. Thank you. And then simplifying, we get T of n over 8 plus 2. Okay, I'm gonna just repeat the steps that I've done so far. And so here we want a formula for T of n over 2. Because we have T of n over 2 in this original formula, T of n over 2 equals T of n over 4 plus 1, and then plus this right here corresponds to this in our original substitution, then adding 1, simplifying that 1 and that 1 plus 2 like that. Here, T of n over 8. We want a formula for T of n over 4 because we have a formula for T of n over 4 right here. And substituting n over 4 into this n over 2, we get T of n over 8 plus 1. The stuff inside of this blue right here corresponds to this right here. And then the plus 1 over here corresponds to this plus 1. Simplifying, we get the T of n over 8 right here. And then the plus 2 comes from this one and this one being added together. So you'll notice, yes, that we have a plus 2 and a plus 2 over here. Both of these two things are the same. And then what's different is that inside of here, we have an n over 8 and an n over 8. Did that answer your question somewhere in there? Yeah, and then so then our next goal here is, now that we have a formula for n over 4, we could substitute that in. We could take this right here, take this thing right here, plug it in for that, and then our formula for T of n over 2 would look something like T of n divided by 8 plus 2. This whole thing right here corresponding to that thing right there plus a 2. And then equals to T of n over 8 plus 4, this plus 2, and this plus 2 together. Yeah. So it's important that these two steps are separate. Here, we're both going back to this original recursive call, and then this final green step right here, we substituted back in to our original formula for T of n over 2. So now we have two different formulas for T of n over 2 right here. And if we substituted these two different formulas up here for our original formula of T, then we'd have 3 different formulas for T of n. Eventually, so the hard part of this iterative substitution, and the part that we're sort of going to gloss over a lot here, is that eventually there's a pattern that comes up. And what that pattern looks like is that t of n will look something like t of n divided by 2 to the I plus 2 times I, where I is our iteration of doing the substitutions. So if this is our iteration 1 of doing the substitution, and this is our iteration 2 of doing the substitution, then these two formulas would hopefully check out over here. I think this needs to be an I plus 1 right there for that math to work out. Going from this step over here to this step over here is not an obvious thing to do, and not something that you're going to have to do. Again, we're going to use the master theorem for our actual runtimes. This is sort of some students find this a more intuitive justification though of why the master theorem is going to do what it's going to do. Any questions about that step into the blue? Apologize, I'm sort of running out of space on the notes here. Question? Yeah, Charlie. So yeah, it's a fantastic point. We still have this original problem that we have t in terms of t, that we've just done a bunch of like weird arithmetic, confusing arithmetic stuff, and what has it actually gotten us? The answer about what it's gotten us, and I'm going to open up another notes page for myself real quick. I will, let's see, I have both of these opened up right now. I'm going to copy over this blue right over here. And then we'll just use this new note page, t of n divided by 2 to the I plus 1 plus 2 to the I. That's equal to t of n equals that. And so the question was, like, what have we actually gained by doing something like this? And the answer is that we do secretly have another formula for our recursive calls and what the runtime is. That this formula right here was only handling the recursive case. But we still have that base case to think about. And the base case, in this case, is going to be t of 1 equals 1. Where am I getting this from? Coming back over here, our base case happens when the length of our list is a constant size. In this case, the length of the list equals 0, and our runtime is equal to 1. So the thing inside of the n right here, the thing inside of our t function, this n value right here, this is the size of our list during the base case. So that's going to be 1, that it's constant size. And we're setting it equal to 1. And so that's where this comes from. And vast majority of times, base cases look something similar to this. Where what we do with this now, though, is we can set this, eventually this thing over here in parentheses is going to get smaller and smaller and smaller. As our number of i's gets larger, this thing inside of here will approach 1. So we'll have something like n divided by 2i plus 1 is equal to 1. This coming from setting this equal to that. And what we're going to do, this is going to tell us how many times do we have to sort of run our iterations through before we're going from our original size n down to a final size of 1 or a constant size. We're going to solve here for I. I here is, again, the iteration that we're on. So the number of iterations that we have to do in order for this to be equal to 1, in order to get down to our array that we're working over to have just one element in it. And doing that, n equals 2 to the I plus 1, multiplying both sides by 2 to the I plus 1, taking the log base 2 of both sides. Log base 2 of n equals I plus 1. And then I equals log base 2 of n minus 1, which is just equal to theta or big O of log of n, simplifying right here. So we sort of saw intuitively, again, last time that binary search, because it is chopping the list in half each time, or in this case, chopping the array in half each time, it only needs a very short number of a very small number of steps in order to work through the algorithm. And here we can see that it is the logarithmic number of steps. And this is, again, what we were saying beforehand was going to be the runtime of binary search, how many iterations it takes. We also said that each one of those iterations takes constant time. And so because it takes constant time, then the final runtime ends up being log of n. Did that sort of answer your question, Charlie? Yes. So the question is, what exactly is I here? The I was, each time we did one of these recursive substitutions, I added the 1 over here. It was the fact that we did 1 recursive substitution right here. The 2 over here was the fact that we did 2 recursive substitutions. And then, yeah, so I is the total number of these recursive substitutions that we're doing in order to get this thing inside parentheses to get as small as possible, or to get it down to the base case, which is 1 in this case. So the question is that here I is somehow suggestive of iterations because we use I for iterations. And so it is like an iterative count, how many times I'm iterating the recursion. We're using the word iterative right here for iterative substitution because we're doing something over and over again. But this is a recursive procedure. If this was all confusing to you, then that's okay. You're not going to have to do any of this. We'll see that the statement of the master theorem is going to also, it's going to have a lot of notation in it. But once you master that notation, it's going to mean that you're not going to have to go through these steps and solve these runtimes, keep track of all these variables, make this jump to this conclusion over here, and then make this other jump, the jumps that we did down here. You're not going to have to do those steps. This iterative substitution ends up being the way that this master theorem is proved, but you're not going to have to actually do that in this class. In this class, we'll just jump straight to the end and focus on the master theorem. The method 2, master theorem. Yeah. One of the goals of showing this is to help justify that, like, even though the master theorem also seems complicated, it's saving you a bunch of these other steps, a bunch of formal details that you won't have to think about. So hopefully you buy into this idea that the master theorem is going to be the simpler technique for solving this problem. We're going to next go through this master theorem and how to apply it to the binary search situation. zoom in here. I'm currently on our, so the master theorem Wikipedia page. The handout that you have starts with this generic form right here is where I started printing. And you can see that this right here, when they're talking about a generic form, this is the that T sort of formula that we had before, but rather than having concrete numbers everywhere, they have just variables A, B, and this f of n over here on the right-hand side. I'm going to come back over here. And what we need is our original T of n was equal to T of n over 2 plus 1. This is what we got from the runtime analysis before trying to solve this equation. The iterative substitution was our first attempt to solve this equation. And the master theorem is going to be our simpler method for solving this equation. The generic form of the master theorem, copying from Wikipedia, T of n equals A T of n over B plus f of n, like this. And so for our particular problem, this in blue is equivalent to this in red if we set A equal to 1, B equal to 2, and f of n equals to 1, like that. If we do that, then substituting these values here into the red would give us the blue. This is going to be the hardest part, or maybe there's two hard parts of using the master theorem. This is the first hard part. Just figure out your A, B, and F. And hopefully that's not too hard, at least for this problem right here. Any questions on where those three variables came from? Okay, the next step is there is this formula for C sub crit, C-R-I-T, right here. Should be the very bottom of your front page. This crit stands for critical, and we have to just calculate what that is. So C sub critical equals log base B of A. So do that right here. C sub critical equals log base B of A. So the log base 2 of 1. And we know from logarithms that the log base anything of 1 is just going to be 0 here. So our critical exponent for this problem is going to be 0. This big table down here then is going to tell us exactly what the runtime is of our algorithm, depending on how this critical exponent, C crit right here, relates to this function f of n. And we're going to have to, once you're really comfortable with your big O notation and the difference between your O's and your thetas and omegas, this will be easy to read through and understand. But we're going to walk through that carefully right now because it is easy to get confused about why there are O's and thetas and omegas and what we're doing in each of these checks. At a high level idea, the way to read this table is that this column right here, the second column, this is the one that we're going to be checking with to compare our C critical and our F functions. And for each function that we'll have in this class, it will fall into one of these cases, case 1, case 2, or case 3. And based on which case it falls into, the master theorem will give us a runtime for our formula. For this problem right here, again, the two things that are most important to check are this, we'll be comparing F and C critical. And it'll turn out that this is going to be a case 2 problem. And so let's walk through and see exactly why that's the case, why it is. Here in case 2, it says when f of n equals theta in subcritical log k of n. So I'm just going to rewrite the condition over here for case 2. It says f of n equals theta of n c crit log to the k of n. This is just copied right here. I just copied this formula in red from the condition right here in column 2 of our table. And this is, again, case 2 that we're looking at. Case 2 is going to be the most common case. I think it's the easiest to understand. So when you're working on problems, this is a good one to check first before you move on to other cases. This k right here, well, let's see, all these variables except for k, we know what they mean. The n, again, is our size of our problem. This is something that is varying. It's the input to our function over here. The f function is given to us as part of the problem. The c critical is something that we calculated based on a and b. The only thing that we don't have here is this k, and we get to choose this k to be whatever we want. We choose k. And we have to figure out, is there a way that we can choose k so that our f function will be equal to theta of something like this on the right-hand side? We know that c critical, so I'm going to just substitute the values we know right here. We know that, so f of n, that was just equal to 1. That's equal to theta n. We know that c critical is equal to 0. And then log k n. This n to the 0 simplifies, goes away to be just 1. It's equal to 1. And so this whole thing will be equal to theta of log k n. And we need to choose a k value or figure out a way to choose a k value so that this thing on the right is equal to this thing on the left. And it turns out that if we select the k value of 0, select k equals 0, then this whole thing will simplify to just 1, and we'll get 1 equals theta 1. This is a true statement at this point, so we do satisfy the condition for problem 2 with k equals 0. When I do that, coming back over here to the master theorem here, the third column over here, the master theorem bound column, tells me what my actual runtime is going to be, what the solution to t of n is going to be. So we get t of n equals theta of n, I'll just write it out again over here, our solution. First, just copying from the Wikipedia entry that t of n equals theta of n c critical log k plus 1 n. And we know the n to the c critical, that just simplifies to 1. We have k value equal to 0 up here. So this is equal to theta of log n, like that. The statement of the master theorem over here is a little bit complicated. There's a lot going on with these 3 different conditions, the O versus the theta versus the omega notation here. We've only taken a look at this middle condition so far with the theta. It might seem a little bit overwhelming getting used to it, but hopefully with this first, I don't know, very high-level quick example of iterative substitution, you're getting the sense that the master theorem is going to be faster and easier to use, at least eventually, than trying to do things by hand manually. That all of these steps here, there was sort of like nothing clever going on. It was all just mechanical things that we had to do to figure out our variables, plug it into C critical right here, and then plug it into case 2 to see if it ended up being true. It did end up being true, and so we got our solution. Just sort of plug and chug. Any questions about how we did that? Yes. Yeah, so we're looking at this formula right here, and to the left right here, we have log base b of a, and this formula right here is just rewriting this thing over here in words. When it says the log of the number of subproblems, this number of subproblems is the A value. The A value right here is the number of subproblems. And then this relative subproblem size is the base B right here. The base B over here determining how big each of these subproblems are. And this is, so combining, substituting those definitions, also with the definition that log base B of A is just log A divided by log B in any base. Did that answer your question? Or? Yep, that's okay. Question is, where did we get the A and the B and the F values from? And the answer is, when we were first looking at the problem up here, we were going through annotating it with our O of ones and getting our recursive call. And we decided that the recursive relation for this function is the T of n equals T of n over 2 plus 1 right here. Not thinking about the master theorem or the iterative substitution, just thinking about the runtime analysis that we already know. And then we used the master theorem to solve this formula right here. What we're going to go through again next is recreating another one of these formulas where we're using the list data structure being substituted in instead of the array data structure. We'll see that it'll end up giving us a different runtime formula down here, a different recurrence relation. We'll solve that with the master theorem and get a different runtime. So if you have more lingering questions about what exactly are all the steps that we followed to do this, then hopefully, again, we'll just be redoing them all in class right here. Hopefully that will help crystallize exactly what's going on for you. Before we go through and do that, are there questions about this logarithmic runtime? Yes. Exactly. Exactly. The only thing creative that you have to do in this is figure out, is there a K that's going to work to do this? And it's always going to be obvious. Like if there's no n over here, then K is going to be equal to 0. Or if there's like log n, then K will be equal to 1. Okay. I'm going to delete the notes that we have up here for the array case. And again, we'll walk through this with the list case and see what exactly the differences are. In terms of the original runtimes up here, so now we're working with the list instead of the array. The base case still was O of 1. All of our if statements and lengths, all these are O of 1, O of 1, O of 1. The only thing that was different between the list and the array is the slicing operation. Again, here's where the slicing happens. And these slicing operations, so again, the size is going to be n over 2 right here. And whether you want to just actually write out that this is going to be n over 2 or just saying that the runtime is O of n, either way will end up working just fine. So I'll put this in the asymptotic notation that our slice here for the list is going to take O of n time instead of O of 1 time. And now what this means is, in terms of our recursion, is we have T of n equals still the T of n over 2. This recursive part right here, this is always somehow going to be like fundamental structure of the code without involving your data structure at all. So this is just the structure of the code determines this part. And then the rightmost part will be determined by, again, this is our f of n, all of our constant steps. What are we doing? What are our computations each time? And here, this is going to be the O of n, or the n over 2. The only difference between my list and my array is that this is now linear instead of constant. We're going to go through next and solve this with the master theorem, but are there any questions about why this is linear over here? Okay. I think I have space right here, so I'll just try to fit it right here, solving it with the master theorem. So we have we need to know our A, our B, and our f of n values. Always the first thing that we're going to compute here. And our A is still 1. Our B is 2. Again, these two things come from this like recursive structure of the code portion. So that's not going to change based on the input data types. But the rightmost part over here is going to change. And now we have an n instead of the constant time. I'm going to drop the big O notation right here just so that I don't have to keep carrying it around everywhere. But everything works out the same, whether you put the O of n or just put the inside of it, the n right here. What we always have to do next is calculate our C critical. And again, that's the log base B of A. I'm using the formula right here to calculate the C critical log base B of A. And this is something that is, again, not changing based on our data structure, that it is determined by this A and B, the structure of our code up here. And so that's going to just be equal to 0. I'm going to try to do the case 2 now. The case 2, and we'll see that the case 2 is not going to work. That we're going to try to come up with set f of n equal to this formula over here, and we'll see that we're just not going to be able to find a k that's going to work, and so this second row is not going to work for us. So again, the condition in sup critical log k of n, case 2, f of n equals n c critical log k of n, and all that is inside of the big theta. Forgot to write that. And substituting in here, it's n would be equal to n sup c critical. This thing goes away again, so we just get 1 times the log of k to the n. And one of the properties that we talked about with big O notation when we were first introducing it was that whenever you have a polynomial on the left-hand side, so this is an example of a linear polynomial into the 1 power, polynomial on the left-hand side and a logarithm on the right-hand side, it doesn't matter how big you make this exponent over here, this term on the right will never asymptotically be equal to this term on the left. And so these two things can never be equal to each other. You can never have a log, no matter sort of what you do to it, no matter how big of an exponent you raise it, you can never have that be equal to this thing over here. So that's just one of the properties that you need to know about the big O notation. And again, you could go back to the definitions of theta to justify that to yourself. So case 2 is not going to work. We'll take a look at case 3 next. Case 3 happens to be the one that works for this particular problem. And I also think that case 3 is a little bit more intuitive than case 1 up here. Here in case 3, it's saying when f of n equals omega of c to, or omega of n to the c. So do this in orange, my case 3. f of n equals omega of n to the c, where c is just some number greater than c critical. Write it right here. I don't need to write this, but c is greater than c critical. It's a good reminder right here. And so plugging in for the f of n over here, we have just n, and we need n to be omega of some n to the c value. What can we choose for c? C just has to be anything greater than c critical. C critical is 0. So we could choose, for example, c equals 0.1. 0.1 is greater than 0, and n does in fact equal omega of n to the 0.1. So this omega, again, is a lower bound. We want to pick a formula on the right-hand side over here that is less than the formula on the left-hand side. And this n right here has an implicit power into the 1 power over here. This is a 1. And so as long as this c value over here is less than 1, then this statement will be true. And we're allowed to pick anything greater than 0. So I just picked 0.1 and it becomes true. Whatever you pick over here has no implications on your final formula. Just as long as there is something that works, then you're good. And in case 3, coming back over to the Wikipedia column over here, there's a little bit of a technical detail up here, which you'll be able to ignore for this class. And the important part is this last formula right down here, that T of n equals theta of f of n. T of n equals theta f of n right here. And so our f of n, again, is just the linear function. So this T of n right here is equal to theta of n. If you recall from the lab on Friday, this particular function right here was very slow when you used a list on it. And I did tell you at the time that it had a linear runtime when you were using the list. And it was very fast when you were using the array. And now we have sort of a theoretical justification for why it's slow using a list and fast using an array. Because with a list, it has the theta of n runtime, but with the array, it has the log runtime. Any questions about anything that I did there? Yes. Your question is this right here. What's the base of this? So the question is that when Wikipedia is using this notation of log k to the n, what exactly does that mean? And this is the same as log n raised to the kth power. Good question. Yes. So the runtime of the binary search recursive 2 is linear, the theta of n. Assuming that the XS right here is a list. And if the XS was an array, then you'd get the logarithmic runtime. Question is, why exactly is this equal to theta of n down here? It's a two-part answer. The first part is that this was our recurrence formula. The key thing to notice about this recurrence right here is the f value over here changed from being O of 1 to O of n. So we're doing a lot of work on each recursion. It's not obvious that we're doing a lot of work because it's just a slice right here. But you have to be like very aware of slices with lists, that they're a common way to get your code to slow down. And so we've increased the amount of work we're doing from constant to linear time. Because we have a different f value right here, the second part of the answer is that now when we substitute into the master theorem, we're getting a different answer. We're no longer part of case 2 right here, because there is no value of k right here that will make these two formulas be equal to each other. Going into case 3, our C subcritical is really small, 0 down here. And so we are able to find a C value that is between the C critical and the power over here. And when we do that, we have this lower bound. This thing does evaluate to true. It is true that n equals omega of n to the C. And because this case evaluates to true, then we use this right here, this final formula right here as our runtime equation. And here, this theta f of n, that f of n corresponds right here to the linear runtime. Did somewhere in that answer your question? Okay. Yeah. Yeah, so the question is, where exactly, like, what's the intuition about this f value over here? And the intuition you should have is this is the amount of work you have to do on each iteration of the recursion, or on each recursive call. And so here, the work that we have to do is in green, these lines, we have to check our base case. That's almost always going to be constant time. And then we have a few small calculations down here, which are also constant time. But then this sneaky slice right here makes things go up to linear time. And so it's because we have this slice right here, this work that we're doing, the work we're doing right here is the slice. That's where this linear time comes from. Anything that's like specific to the recursive call itself, like how many times you're calling the recursion, or what the size is. If the size is changing over here from like n over 2 to maybe n over 4, then that would affect your t value over here. But if it's not, this sort of looks like it's affecting the binary search because it's on the same line. But again, this is happening before because we need to evaluate this before calling. So this is part of the work that we're doing on the recursive iteration. Does that answer your question? Right. Question is, once we identified that we're in case 3, how did we go from here to the actual runtime? And the answer is that once you've identified you're in case 3, again, this part up here has some technical condition that needs to be satisfied. This will always be satisfied in this class. It's like weird edge cases relating to infinities sort of things, like weird infinities that might make this not be satisfied. And so you can just jump straight down to this formula right here at the very bottom and say that your runtime is whatever your f value was. So in some sense, the third case over here, it's one of the reasons why I think it's one of the easier cases, because you're just, your f value is whatever your runtime is. 2 is the most important case. This is what most algorithms, most good algorithms turn out to be. So binary search being an example of a good algorithm. And then a lot of bad algorithms turn out to be this case 3 over here. So this like theta of f of n, something that you'll see a lot when you're doing something that you shouldn't do, like the slice of the list. If you go into the binary search recursive up here without the number 2 at the end. Again, this is the one that I was recommending you use to base your solution to the homework that's due tomorrow. Base it off of this one because there is no slice inside of here. And if you were to work out the recursion, the recursive formula for both cases, or rather all 4 of the data structures that you did in the lab, the list, the array, the tuple, and the I guess, yeah, the list, the array, and the tuple, not the deck, you would get T of n equals T of n over 2 plus 1 for the list, array, and the tuple. And we've already seen that if you solve this, then you just get that that's the runtime of log n. So that's why you'll want to use this one to, that's why this one's faster and why you'll want to use this one for your homework. Your homework that is going to be due next week is based off of sorting. And so there's two sorting algorithms that we're going to be going over on Wednesday in class. This merge sort and this quick sort, both are famous for being good examples of recursive algorithms that have more complicated runtime structure. And so next time on Wednesday, we'll be going over exactly what these different columns mean in this table here and why merge sort and quick sort are good. I've given you this under the sorting notes. There's some code down here. I definitely recommend you use this code as the basis for your homework assignment. I've actually given you like this is working code for merge sorted right here. This is one of the functions that you have to implement, and you'll pass like 9 out of the 10 test cases just using this exact code right here. There's a slight extra parameter that's being passed to the function in the homework. So you have to modify this just to handle that extra parameter, but the outline of this code here is 100% correct. Similarly, down here for quicksort, this code is 100% correct for what it does. You'll just have to do one small modification to it to make it work for the to pass the test cases in the assignments. What we're not going to talk about in class is this merged function right here. You're going to have, this will be the hardest part of the homework, is implementing this underscore merged function. The idea of what it does is just that if we have two lists that are already sorted, then it combines them into a final sorting order. My solution for this, so I know I have said bad things about while loops. My solution for this, though, uses while loops, and I recommend that yours does as well. Yeah, on Wednesday, we'll go through explaining these algorithms, go through their runtime analysis, and see how it's different from binary search. But this is a good spot for us to stop for today. If anybody has any questions about any of these things or anything else, I'll be here after class, or I have my office hours later today that you can come see me. But that is it for today.